So I have a question for the first presentation we had done with Gilad. You did mention, great presentation by the way. Gilad, you did mention that with the deep buffer switches could have their own set of problems like jitter. And I wasn't sure how jitter would be a problem there because if you have a very perfect load balancing happening, uh, you might not have that jitter, right? I mean, the jitter happens because of the queue depths build up and stuff, and if it's a perfect load balancing or close to that, you deep buffer or no deep buffer, it shouldn't make any difference.
Yeah. First, let me give you some things to think about. Scheduled fabric, it's not a new thing. It was created for telco applications many years ago. And then later was trying to set it to utilize for storage applications. Now people try to position it for AI. If a scheduled network was delivering what distributed computing application need, that would mean that all of the supercomputers in the world would use that network. That would mean that the top 500 supercomputing list would have all scheduled fabric on that list. Reality is that there is zero there. And there is zero scheduled fabric on the top 500 supercomputers, and there is zero scheduled fabric that is being used for distributed computing on scientific applications. Which means it's not delivering what essentially distributed computing needs. Okay, that's de facto. Another element to think about is that if there would be an iterant solution that solves the need for AI, why would same companies created a consortium called USC to create the new versions of iterant for AI if it's already exists, right? So things are not really working. Okay, now why doesn't it work? Why doesn't it work? The thing is that scheduled fabric first has limitations of how many GPUs, how many nodes you can connect. There is limitations of distance of fabric, for example. It requires doing under subscriptions, for example. There is more links on the scheduled fabric than what exactly goes to the GPUs. But the main thing is, and by the way, there is no adaptive routing until you get to that point, so there is a lot of other stuff. But the fact that you have the switches trying to spread the traffic, the whole idea about scheduled fabric, a scheduled switch network in a sense, is that you break Ethernet into non-Ethernet, right? Small cells, try to spread that. You don't go to the second layer, until you know that the first layer has a space to cover that part, and then you need to rebuild the packet there. So there is, and because of that, you also need deep buffers to kind of get the shock absorbers. Deep buffers create latency jitter in a sense. That's, if you're gonna look on every deep buffer network, that's what we're gonna see. And that means that you have latency differences. And latency differences, you might say, well, for all reduce, might be not that critical part, and that's why we're talking about nickel all reduce operations. People forget that there is a lot of all-to-all operations. And all-to-all operations are very, very sensitive to latency from that perspective, right? So there is no something that, it's gonna find zero. Okay, so when we start to do our development in that sense, we looked on all the options. So, here you get a good load balancing, but you're gonna get jitters and difference in latency is gonna impact all-to-all operations. If you don't go deep buffers, you don't have the good load balancing, right, in that sense. You have lower latency, but you don't get good load balancing because you're using flowlets. So how do we solve that stuff? We don't want deep buffers, we don't want flowlets. All right, so in that case, we say, okay, let's do what people do in HPC for many years. And what people do in HPC for many years is they don't try to fix it on a switch. It's an end-to-end approach. Now, end-to-end approach doesn't start at the NIC level. Okay, it starts at the GPU level. Because the GPU is an algorithm that reflects on nickel. Nickel, it's NVIDIA Collective Communication Library. Reflects on nickel. Nickel reflects that on the nickel. The nickel reflects that on the entire network. Okay, so you start end-to-end from a GPU perspective, then you kind of control and make sure that you run the right algorithm in the right place. The NIC can do direct data placements. The switch can be simple. And the simple as the switch is, it's better for you, right? You don't want large buffer, you want small buffers. Small buffers means that there is not much of latency differences. You want to deal with the hotspots quickly, fine-grained adaptive routing, make it simple. You know, the simple that the switch network is, it's gonna give you more deterministic performance at the end. Sorry for the long answer, but I hope that covers.
Sure, thank you. I have a second question. You did mention about that we have telemetry of the order of microseconds.
That there is, sorry?
Telemetry.
Yeah.
Congestion control, perhaps that's what you meant. Generally, most of these would run end-to-end, that is RTT. So when you said microseconds, did you mean it is able to get that info in microseconds back, or did you mean it's periodically sending every microsecond level kind of probes?
Yeah, so it's a combination. When you do first, telemetry is important because you get sense of what's happening, and you need to go to cases of high frequency telemetry to microseconds in order to understand performance issues on the network, or sometimes it's not on the network, sometimes it's on the node. And we had cases, for example, that we need to go to high frequency telemetry to debug issues on the nodes, for example, to see that there is some high spikes and stuff like that. When you go to hotspots or congestion control, for example, there are things that exist already. There is ECNs and there is indication coming from the switch that mark packets and stuff like that, but it's not enough. And that's why you add telemetry. And what we did, essentially, is creating telemetry probes. And those telemetry probes you can send in a low frequency. Once you start seeing changes, you can increase and actually send in high frequency and play with that. The telemetry probe is a small kind of, think about the probe, a small probe that goes and collect data that the switch puts in hardware and the endpoints put in hardware. So there is no compute or CPUs involved in that part, not the CPU on the switch, not the CPU on endpoint. It's being placed in hardware, that piece of data that says kind of what my status. It goes one way on the data flow, because it needs to suffer the data flow. On the way back, it has its own path. So on the way back, it's guaranteed it's half RTT. Regardless, there is no delays on that part. And that's why I know what's the latency here. And then I get indication about what's the latency is here. And if I see changes here, then I can start controlling the ejection rate that comes from the endpoint. That's kind of how it works.
Got it. So it's basically the frequency at which you send the probes is of the order of microseconds.
Yeah. Now, if there is no changes, you can fall back in sub-millisecond and stuff like that. But once you go into the areas that you see changes, you go high frequency.
Got it. Sure. Thank you so much.
Sure.